in this lecture, I am going to look at a method of representing three-dimensional symmetries, point symmetries, using what is called as a stereographic projection. Now, in this stereographic projection, what we do, we represent axes, we represent motifs, everything on the surface of a sphere. So, here I have a surface of a sphere, and let me put a coordinate system. So, I have this sphere, this circle in the center bisects this sphere into two halves. You can call this as an equatorial circle as well. It forms the equator of this sphere. X and y axes are in the plane of the equatorial circle, while the z axis is normal to the equatorial circle. Then I have labeled some of these things. I have labeled this z axis also as an axis AB, and AB is called as a projection axis, while the equatorial plane is called as the projection plane. So, everything will get projected on a two-dimensional plane. So, let us say that I have a point labeled as 1 on the surface of the sphere. If you recall going back in which when we are combining rotation axes. So, we had put the rotation axis starting from the center of the sphere, and it would intersect the surface at some point, which we also call as a pole. Now, project this point on the projection plane, and that would represent either the motif or it will represent that rotation axis. So, how can I present this, how can I project this point? Well, we use point A as the point of projection. From the point of projection A, draw a line to connect point 1. So, A is connected to point 1 by a straight line. This line will intersect somewhere in the projection plane, and let us say it intersects at point 1 prime. So, therefore, this becomes a representation of this pole 1 on a two-dimensional plane. So, I can take this two-dimensional plane out of the sphere, and I can put this point 1 on the projection plane. Such a diagram is also called a stereogram. So, we will represent all symmetries based on such a diagram. Now, in this case, if I consider this 1 prime to be a point in the upper hemisphere, so it will be represented as a dark or a filled circle or a black dot, and this is a representation of symmetry 1 or no symmetry at all. But now, imagine that I have a two-fold rotation axis which is along projection axis AB. So, what will happen? The pole 1, the rotation axis will rotate this pole 1 through an angle of 180 degrees, and we will replicate another point, another pole on the surface of the sphere, which I label as point 2 or pole 2. Now, we do the same thing as we did with pole 1, project this pole 2 or point 2 onto the projection plane using the point of projection A. So, we join again the point of projection A to point 2 with a straight line. Now, this line will also intersect the projection plane, and let us say it intersects at 2 prime. So, I have rotated 1 to 2 through a angle of 180 degrees, and this point 2 gets projected to 2 prime, forming a stereogram which should be something like this. This line that I have drawn joining 1 prime and 2 prime is just drawn for reference, it is not required. I can just show it as just 2 points, and the two-fold rotation axis itself gets projected onto the center of the stereogram. So, therefore, this becomes symmetry 2. that it has a two-fold rotation axis. Now you can imagine that I can have three-fold, four-fold, six-fold, all of them would appear, and the number of poles that will be shown would be more. For example, in three-fold, I'll have 3 poles. So 3 points would be there in the stereogram. Four-fold, there will be 4 points. Six-fold, there will be 6 such points, which are rotated through 60 degrees. Now let's add a symmetry element to this, another symmetry element to it. And what I've done, I've added a mirror plane, and now this mirror plane, the projection plane, is also the mirror plane now. Now what is going to happen is, the poles 1 and 2 will get reflected by the mirror plane. So poles 1 and 2, which are in the upper hemisphere, will get reflected to the lower hemisphere or the bottom hemisphere like this. So these poles 3 and 4 are a result of the reflection as a result of the mirror plane, which is lying in the projection plane. Now I need to project these poles 3 and 4 as well now onto the projection plane. Now suppose I use the point of projection A, then if I draw a line A joining to 3, this line will go outside this equatorial circle. Of course, you can consider the projection plane to be infinite, then it will intersect somewhere on the projection plane. But as a pole comes closer and closer to the point of projection A, further and further away the projection of that point would be on the projection plane, and therefore that is not a satisfying solution to project these points using the point of projection A. So what we do is, now for the points lying or the poles lying in the lower hemisphere, we will use point B as the point of projection. So now point B will be used as the point of projection, and we will connect the poles 3 and 4 to the point of projection in this fashion, and these lines now will intersect within the equatorial circle. And it is very interesting to note that any reflection that occurs, these lines will intersect at 1 prime and 2 prime from where these points were reflected. This will always be the case. So now I have points 3 and 4, which are at the same the projection of points 3 and 4 are at the same location where the projection of the points 1 and 2 are. So how do I represent this? So this is represented by an open circle. Open circle means that these are projections done for those poles which are at the bottom hemisphere. Now this, and you also see that the stereogram itself, the circle of the stereogram, is also shown as a dark black line to indicate that it is a mirror. So 1 prime is reflected to 3 prime, 2 prime is reflected to 4 prime in the stereogram. So you can easily read this, and I used, in fact I should also say that 1 prime can go to 4 prime through an inversion center. And where is this inversion center in the sphere? The inversion center is right at the center of the sphere. So pole 1 can be inverted to pole 4 in this manner. So you may make a bit of a correction, otherwise it is okay. The numbers here and numbers here are a bit out of order, but otherwise the inversion center shown on the stereogram will be in the center of the circle. The next thing to do would be as follows, that this particular point group is represented as 2 upon m. So this 2 over m. Now what this over oblique line, over like a division line, it shows that the mirror plane is perpendicular to the two-fold rotation axis. And I have shown this open circle in red to indicate a change of handedness. So we will consider black, let us say, as right handed, then we will consider red dots or red circles as left handed. So this is the kind of legend I have made, that the up points, up means in the upper hemisphere, the dots filled circle indicate they are in the upper hemisphere, and black means right handed, red means left handed. Same thing, down means in the lower hemisphere, open circle means that these are projections from the lower hemisphere, and again black is right handed and red is left handed. Now, let us come to another situation. I had again start with this point group 2, in which just a rotation axis at the center. But imagine now that, let us say, along the y axis also I have another two-fold rotation axis. So, now what will happen is, this two-fold rotation axis will rotate the points 1 and 2 about the y axis, and as a result I will get two new poles in the lower hemisphere through a rotation of 180 degrees. So, now these poles will also be projected onto the projection plane, and they will be projected using the point of projection as B. And another thing to note is that, and we have already done this, if I have two two-fold rotation axes, there has to be a third two-fold rotation axis which will be at 90 degrees. So, this is combination of 3 rotation axes, and this you can also see using the pole using that how the poles rotate. So, this two-fold rotation axis will also rotate these poles in a self-consistent manner. On the stereogram, the points or the poles 3 and 4 get reflected by open circle, and on the stereogram other two-fold rotation axes will also get projected, and they will get projected in this fashion. So, now I have along the x axis there is a two-fold axis, along the y axis there is another two-fold axis, and in the center there is a two-fold rotation axis which is perpendicular to the plane or perpendicular to the two-fold axis along x and y. Now, if I look at the stereogram alone, then 1 prime can go to 3 prime by the two-fold rotation axis along y, 1 prime can go to 4 prime by the two-fold rotation axis along x, while 1 prime and 2 prime and 3 prime and 4 prime can overlap or self coincide by the two-fold rotation axis in the center. So, now what we can do now is, incidentally, the point group that we have formed here is the point group 2, 2, 2. And what we can do now is we can now skip drawing things in 3 dimensions on the surface of the sphere. We just do everything from now on a stereogram, and let us start this. So, now let us just consider a 2-dimensional plane in which, let us say that I have to show a roto inversion axis 1 bar. So, I start, let us say, with a point out here. This is in the upper hemisphere, so it is up. Now, a roto inversion axis 1 bar, remember we had seen in the last lecture, 1 bar would mean 360 degree rotation. So, 1 fold roto inversion, 360 degree rotation, we will come back to the same point and then invert. So, this point will rotate through 180 degrees, and invert means it will go in the lower hemisphere, it will show up as a circle, and with the color change I have done to represent that this is a left-handed object. So, I have gone from right-handed to left-handed and through 1 fold roto inversion. But now, what is 1 fold roto inversion? If you think about it a bit, 1 fold roto inversion is nothing but there is a inversion center in the center of the sphere. In the case of the stereogram, there is an inversion center in the center of the circle or the stereogram, and which is represented by a small circle. So, this is, we will call this as center of inversion, and in fact, instead of calling this as a 1 fold roto inversion axis, we can simply call it as inversion symmetry, a simple pure inversion symmetry. Now, let us consider the second roto inversion axis, 2 fold roto inversion. I again start with the point up in the upper hemisphere. I rotate this time through how much? I should rotate this by 180 degrees. So, rotate through 180 degrees, come at the top here in the stereogram and then do an inversion, and I come back on top of or the below the first point. So, again because of the inversion there is a handedness change. Now, 2 bar, can it be represented by some other point symmetry? Yes, it can be. If I consider this as a mirror, if I consider this as a mirror, then it is simply, so mirror is in the projection plane. So, there is a point up and it reflects down, and we will get both the points in the projection eventually on top of each other. So, therefore, this is nothing but simply the point group M. Now, consider this time 3 bar. So, I have a threefold roto inversion. I again start with a point in the up position, upper hemisphere. Now, I rotate by 120 degrees. So, if I go here, this is 90 and then another 30 degrees will give me 120 degrees, and then from here I invert, and when I invert I will go down and come here with the handedness change. Now, starting from this point I go again 120 degrees. So, this would take me, this is 60 roughly, and then another 60, I will come here and then invert. I go from down to up again with the handedness change. So, I will come somewhere here. Now, I rotate again by 120 degrees. So, I will come out here, but I do not put the point here. I invert, and when I invert I will go down. So, I will go down and come out here. Then now I will, this is the down position, handedness change again. I will rotate again through 120 degrees, I will come here and then invert to go to the up position. So, I would come here. Now, I keep repeating this, then I go another 120 degrees. So, this one, and I will come out here. So, I have here just, so I will go 120, I will come here, then invert, I will go down and I would be here. Now, I go another 120 degrees. So, that would take me out here, and then I invert, I will go up and I come at the starting point. So, my diagram is complete. Once I reach the starting point, that means it will just keep repeating. So, the diagram is now complete. Now, what do I see in this? Well, I see clearly that there is a threefold proper rotation axis, a proper threefold rotation axis with no, and anything else I see? I also see an inversion, that all points, the black and the red, if you focus, they can all be go into self coincidence by inversion, and their handedness will change appropriately. So, for example, this one, if I invert, so this is down position, it goes to up position and the handedness changes correctly. So, therefore, there is an inversion center as well, which I represent by a small circle. So, if I look at it, this threefold roto inversion actually can be decomposed into a threefold rotation axis and inversion. So, I apply both of them individually to get this diagram. Now, let me consider a six-fold roto inversion now. I start again in the same way, I start with this point, up point, and then I rotate, and this time I rotate through 60 degrees because it is a six-fold roto inversion. So, six-fold would take me out here and then do an inversion I come here. Then I rotate through 60 degrees, come here, and then do an inversion. I go to the up position. I rotate through 60 degrees in the up position, and then invert. I come here, I go to the down position. From the down position, I rotate through 60 degrees, invert, I will go to the up position, and the point will move at this position. Let us do another rotation from the up position, 60 degrees, invert, I go to the down position, handedness changed, another 60 degrees, and then invert, I come back from where I started from in the up position, and therefore, this diagram now is complete. If you notice this, there is a mirror here just by looking at the points up and points down. They can, by mirror plane in the projection plane, would bring all these points in self coincidence. Now, a six-fold roto inversion can be represented as a, first I draw the hexagon to show the six-fold part of it, but you see that there is another rotation which is possible, which is a three-fold. So, there would be, so the six-fold roto inversion is, graphical notation is a hexagon with an inscribed triangle. But one thing is very clear from this diagram, that this 6 bar can be represented by this particular symmetry 3 upon m, or this particular point group 3 upon m, because there is a three-fold rotation and there is a mirror plane perpendicular to three-fold rotation, which will give me the same stereogram. So far, what we have seen is all the rotation axes we have been able to represent it by some other point symmetries, that either inversion, rotation, mirror, or combination. But let us now consider one more which I have skipped. So, I have done 1 bar, 2 bar, 3 bar, and 6 bar. I have skipped 4 bar. Let us consider 4 bar. Again, I start with the point in the up position. This time I am going to rotate through 90 degrees. So, my rotation through 90 degrees would take me here and then invert. I will go in the down position with the handedness changed. Then I rotate through 90 degrees from the down position and invert. I will go to the up position at the top. I do another now rotation starting from here through 90 degrees and go to the down position. I rotate again 90 degrees from the down position, I invert, I go to the up position, I come back where I started from. And this is an interesting situation. What do I see here? I see also a two-fold rotation symmetry at the center. You can clearly see at every 180 degree rotation, this pattern will come into self coincidence. So, how do I represent this particular symmetry? So, since this is 4 bar, so let me first make a square symbol, but there is a two-fold inside. So, I will inscribe the two-fold sign inside the square to represent 4 bar. The interesting thing about this particular pattern is that this cannot be decomposed into other point symmetries. So, in this case, in this situation, 4 bar is a unique roto inversion axis among the crystallographic axes. So, this will be treated differently from the other roto inversion symmetry. Thank you.